Okay. Has it loaded by chance? Maybe. Perfect. Okay, so quick recap because you missed it. We care about protonation states in kind of the grand scheme of this equation, or this is one of our equations, and it's because we care about which of these of the two functional groups, right? Which state is the dominant state, right? When our protonated, press button. What the heck? Wow. I don't know what it's doing. That was weird. When the protonated state is dominant, it can both donate and accept a hydrogen bond. When it is deprotonated, it can only accept a hydrogen bond. However, it can also engage in something like an ionic bond. Okay, so a good application of this is for our ionic bonds is let's say we had an amino acid do an H2, we'll do lysine. Okay, at physiological pH, lysine is positively charged, and this can engage in an ionic bond with a aspartic acid residue. Let's see, it will be okay. So we can get this ionic bond here that would otherwise not exist if our dominant protonation state was protonated. So this is why it's super important that we be able to distinguish between these two, because this has some very important ramifications for things like tertiary structure and quaternary structure, right? Because these are where we start taking into account the R groups, different color, the R groups of our amino acids and the interactions that take place between them. Okay, so this is very important ramifications for our R groups. Okay, so looking at the Canvas document, so if you need it, main page, go to Files, and then under Files, there's one kind of in the middle. It says pKa workshop.pdf. That's the one we'll be looking at first. This one will just kind of take us through pH and whatnot. pH and pK, like the basics, and then we'll transition from that into practice test questions. Okay, so the first question says, what is the relationship between pH and H+? Well, so in a solution, right, we have this certain amount of H+. Okay, it's going to be floating around in solution. Okay, might also hear this referred to as the proton concentration, because H+, right, a hydrogen is a proton and an electron, and so if we remove an electron to get a positive charge, we just have a proton that's left over. Okay, so if we have a solution and it says like our hydronium concentration is 1 × 10⁻⁶, that is a terrible number to work with, and that's a really easy number, right? What if it were 3.82 times 10 to the negative, 4.8, right? These are not nice numbers to work with at all. And so what we do is we can simplify it by using the negative log function. Okay, so if we take the negative log of the H+ concentration, I also should make a note that H+ for our purposes is the same thing as H3O+. So if you see these two, treat them as the exact same. So now back to our original equation, right? Negative log of the concentration of H+ will now give us, it should be a base 10, although technically that's implied, but I'll be clear. This will give us a much nicer number. And for most of the things in this class, it will be our pH range will be between about 0 and 14. You can have pH below 0. You can have pKa's below 0. So I think like hydrochloric acid as a pKa somewhere around like -2-ish. And you can have pHs and pKa's above 14. So really, really strong bases, which if you take OChem, such as like LDA, around like 40 or 50 for their pKa's. Okay. But for 99.9% of the things in this class, we're going to be dealing between 0 and 14. And in general, our physiological pH is about 7.4. Okay, so that is right about neutral, because neutral is a pH equal to 7. Okay, so now if we have a pH scale and we have 7 in the middle, this is neutral. Below 7, we are actually increasing the H plus concentration. So if we're increasing the H plus concentration, we're making this area more acidic. So now our pH will be decreasing. So H plus concentration is increasing. Our, as we go this way, our pH is decreasing, which is completely counterintuitive, but that's the nature of this negative log scale. And then vice versa, right? As we go above 7, so we go towards 14, we're decreasing our H plus concentration. It'll be more basic, and we're increasing our pH. Okay. So, increasing pH means we're decreasing the H plus concentration. Okay. So remember, pH is just an easier way to work with your H plus concentrations. Now, very rarely are you going to be asked to actually calculate the pH. So you wouldn't be given an H plus concentration and be asked to calculate the pH. That's for Gen Chem. We don't really care about that. We care about the applications of this. Okay, so comparing pHs together. So if I asked you, what is the difference in H plus concentration of pH 3 versus pH 4? Okay, well, we're dealing with a negative log base 10 scale. So that means every 1 unit is a 10-fold change, or a 10 times change. Okay, so if we're going pH 3 to pH 4, you guys can put in the chat or think in your head, is this a 10 times increase or a 10 times decrease if we're going from pH 3 to pH 4? Correct. It is a 10 times decrease. Okay, so 10 times decrease in H plus concentration. Okay, and now if we did pH 4 to pH 3, is this a 10 times increase or 10 times decrease? Ten times increase. I believe he even said at one point that this will 100% be a question on the exam. Yes, I've seen a lot of his exams, a lot of exams just in general, and this is a very common question. Okay, so then the next part or application of this is if we have pH 3 versus pH 5. Okay, so if we're going from pH 3 to pH 5, is this a 100 times or a 20 times increase? Or sorry, decrease in H plus. So if we're going pH 3 to pH 5, is this a 100 times decrease or 20 times decrease? It's a 100 times decrease, right? Because every single one, so going to 4 is 10 times. Going 4 to 5 is a 10 times decrease. So we do 10 times 10 equals 100. Okay, so we're dealing with a 100 times decrease in our H plus concentration. Okay. Any questions so far? If I don't see anything, I won't, or I'll assume that you're good. Perfect. Alrighty, so first question, what is the relationship between pH and H plus? To go from H plus to pH, we take the negative log base 10, and this is just a way easier method of comparing our H plus concentrations. Okay, which pH indicated more H plus, pH 3 or pH of 8? So we'll compare the two. So question 2 says, right, which pH has more H plus, pH 3 or pH 6? Well, if we look at our scale, we know that as we get closer towards 0, we're increasing the H plus concentration. So which one has a greater H plus concentration? Correct, 3. Okay. And now we can go one step further and ask, how much greater? What is the fold increase in H plus concentration between the two? 1,000 times, right? So to go from 6 to 5 is 10 times. 5 to 4 is 10 times. 4 to 3 is 10 times. 10 times 10 times 10 is a 1,000 times increase in our H plus concentration. Perfect. Okay, so that was question 2. Here was question 1. Moving on to question 3. We have a membrane. Looks like this, where each of these positive charges is a relative proton. Which side of the membrane, side A or side B, has a higher pH? Correct answer is B, right? Because higher pH means lower H plus concentration. Okay, and so this had asked, what is the higher H plus concentration? We would say, which side has the higher H plus concentration? It would be side A. Okay. Now, once we get into metabolism, this idea is actually going to be very, very important, because what we're going to end up talking about is how we have this process that pumps protons across a membrane. So we get a very high proton concentration here, very low proton concentration on this other side. And we're going to have an enzyme that can take these protons, and when we learn about this thing called diffusion, this process of this H plus going back across the membrane to equalize the pH, equalize the concentrations, this is what we'll call exergonic. In other words, it releases energy. So this idea here of differences in pH is not just going to be important for pH and pKa, but is also the heart of a huge chunk of metabolism. Okay. So that's where we're going with that, and that'll be midterm 2 material. Okay. I might be running out of room. There we go. Okay, so question. What are we on? I guess there really isn't a question. Functional groups and pH. Okay, so we're given the stereotypical acetic acid. Okay, and it asks us, circle the protonated and underline the deprotonated acid of the reaction. So the protonated one is going to have the proton attached. And so our protonated one does circle. Okay, we would circle this side and underline that side. Okay, the right-hand side. Okay, which way will the equilibrium shift as H plus increases? Okay, so now if I increase the amount of H plus, we're essentially increasing the amount of a product we have. To answer this question, we need to take a quick side tour to Le Chatelier's principle. Okay. And so if you disturb a equilibrium reaction, it will shift to the side opposite of the disturbance. Meaning if you increase the amount, so if we have A plus B goes back and forth with C plus D, and this is at equilibrium, if we increase the amount of C or D, what's going to happen is we're going to momentarily increase the rate of the reverse reaction to result in a net reaction like moment rate that favors the formation of A and B. Okay, and you can think of this in terms of, in order for two molecules to react, they must hit each other. And so by increasing the amount of D artificially past equilibrium, you're increasing the amount of molecules you have that can hit each other, right? You're increasing the amount of concentration you have that can hit C to then form A and B. Okay. So we'll favor the opposite side when you're increasing. Now, when we decrease, so let's say we decrease the concentration of D. What do you guys think is going to happen? Is the forward reaction as written, so left to right is forward, or the reverse reaction going to be favored? So as we decrease the concentration of D past equilibrium, will the forward or reverse reaction be favored? It is, in fact, the forward. Very nice job. Okay. The reason why is, remember, same thing as we did earlier. In order for molecules to interact in a chemical reaction, they need to hit each other. So if we decrease the amount of D, there's now less of that molecule that can interact with C to form A and B. So what happens is the rate of formation of A and B momentarily decreases, whereas A and B, that rate of formation to form C and D stays the same. And so A and B will become the dominant part of the reaction, and so it'll form more C and D. Okay. So if we increase, we favor the opposite side. If we decrease, we favor the formation of that side. And so the important change of this is that if we alter just D, right, what's going to happen is we are increasing the concentration of D, but as I'm talking about reaction 1 right now. We increase the concentration of D. This will favor the concentration or the formation of A and B, which will then cause the concentrations of both C and D to decrease. So after, we'll have a greater concentration of A and B, and we'll have a decreased concentration of C and D. Because we've now favored the formation of A and B. So this is after equilibrium. And so what that means is we would then have more A and B than we originally had C and D, in terms of if we were to assume their concentrations were equal, which is not always true. But we can then make a general statement of just, okay, after our change, if we compare it to the equilibrium, we will have more A and B from their equilibrium or their initial equilibrium concentrations, and we will have less C and D compared to their initial equilibrium concentrations. Okay. And then for reaction 2, if we are shifting the reaction to favor C and D, we're going to increase the amount of C and D we have due to this favoring by the reaction rates, and we're going to decrease the amount of A and B we have. Okay, so this is Le Chatelier's principle. Now we can apply it to our pH and pKa by means of this H+. Okay, so if we were to increase the amount of H+, well, we're essentially doing our reaction 1 here. Okay, so if we increase the H+ concentration, we're going to favor the reverse reaction, which means we're going to now get more of our protonated state. And so if we're getting more protonated state, remember, you can only have, 100% of your molecules here. Okay, so of our functional group, if we have 100 molecules and we're making more of our protonated state, by very definition, right, of 100%, we're getting less of our deprotonated state. Okay, and then in the other scenario, if we decrease the amount of H+ concentration, we're going to favor the forward reaction, which means we're going to get more deprotonated and less protonated. Okay. Now, I do want to clarify that this more protonated and less deprotonated and less protonated and more deprotonated is in reference to itself. So it's initial equilibrium and then the equilibrium state after of just this functional group in its specific protonation state. We now want to go from here to figuring out which one is the dominant species. So at what point does the less protonated and more deprotonated for the second reaction get to the point where it's not just we're getting more of our deprotonated form, but we're getting so much more that is now the dominant protonation state. And so this is what's going to drive us into pKa. So that is question 4, question 5, question 6. The same thing applies. I guess, sorry, question 6, that was 4 and 5. Question 6 and 7 are the same thing, except with the amine. So we have R and H. We're going to come back to the pKa in a second, but I do just want to complete the entire worksheet. Okay, so circle the protonated base. Here's our protonated base. And underline the deprotonated. Okay, so with amines, it's very important to recognize that this guy does have a proton, but it is not the protonated state because it does not have the positive charge. So our protonated amine will have that positive charge. Okay, and so which way will the equilibrium shift as H plus increases? So if we increase the amount of this, we're favoring the opposite. So we will increase the amount of protonated and decrease the amount of deprotonated. Okay, and then if we decrease the H plus concentration, we're going to form what's it called? What's the word I'm thinking of? We are gonna favor. We're gonna favor the formation of more H plus to balance that equilibrium. So we're gonna get more of our deprotonated and less of our protonated. Okay. And then the next part of this is just remembering that decreasing H plus concentration is the same thing as increasing our pH. So this question can be asked in either way. You know, what happens when you increase the pH? What happens when you decrease the pH? It's now just asking you, do you know this relationship? And then can you apply that relationship back to our original equation? Okay, so coming back to here with our initial one, to pKa. Our pKa is going to tell us which of these two states are dominant at a given pH. Okay, so when we have a pKa, and for acetic acid, it's about 4.74. pKa is a measure of acid strength. And how we get this is taking the negative log of the Ka. And the Ka is just the KEQ of an acid. And so what this is this is the equilibrium concentrations of an acid reaction. Okay. So it's a measure of acid strength. We derive that from the negative log of the Ka, and we do the negative log for easier numbers. And we get the Ka. It's just a fancy term for the KEQ of an acid. And the KEQ is the measurement of the EQ concentrations of a given acid reaction. Okay. So when we have our pKa equal to our pH, so our first step is pH is equal to pKa, or pKa is equal to pH. What we're saying is the strength of the acid equals the acidity of the solution. In other words, nothing is really favored, right? They're equal to each other. And so what that means is we're going to end up getting 50% deprotonated and 50% protonated. Another way you can derive this is by using the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of the conjugate base over the conjugate acid. Okay, and so if our pH is equal to our pK, that means our log of this guy here must be equal to 0, right? In order for pH to be equal to pKa, this guy must be 0. And in order for the log of something to be equal to 0, we must be taking the log of 1. And so by mathematical concepts, that means the concentration of the deprotonated and the deprotonated over protonated is equal to 1. And so now what we can do is we can multiply both sides of our equation by the concentration of HA. That'll cancel that out. And what we'll be left with is the concentration of A minus is equal to the concentration of HA. So that is how we mathematically show this relationship here. Okay, because when they're equal, right, what you can do is to calculate the percentage of your protonated and deprotonated. You can take the amount of protonated or the amount of deprotonated in solution, and what's it called? Divide it by the total amount in solution, which you only have two possible states, protonated and deprotonated. So our percentage is equal to the what's it called? The amount of deprotonated over the amount of deprotonated plus protonated. But because these are equal to each other, we can say that we have concentration of A minus over the concentration of A minus plus the that's not A minus. A minus plus the concentration of A minus. I'm running out of room. Okay. And then we have something plus something else in the denominator that is that same thing. So we effectively have something plus itself. So that's just 2 of that thing. Oh my gosh, not HA minus. A minus, there we go. And now we have A minus over A minus. We can cancel that out. And what we're left with is 1/2. So our percentage is equal to 50%. Does that make sense? You wouldn't be expected to use the Henderson-Hasselbalch equation, not just for your upper dip bio classes, but if you're a math person and perhaps you've taken Chem 2A, I think it's Chem 2A, then you're experienced with this, and this might help you figure out why when pH is equal to the pKa, we're at 50%. Okay, so now what we're going to do is our step 2, and we're going to say our pH is less than our pKa. Also, if you have a question, please just ask it. You can either unmute. Actually, did I give you guys permission? I think I gave you guys permissions to unmute. I hope I did. Or you can just put it in the chat if you have a question. Oh, darn it, really? God, hold on. Okay. If you guys have a question you would like to unmute, just request to speak. I'll have to figure out how to give you guys perms to just unmute later. Oh, well. Anyways, or you can put it in the chat. Anyways, when our pH is less than our pK, another way of saying this is we have a lot of H plus in our or a lot of H plus in our solution compared to our acid strength. Okay, so if we were to look at our, actually, I'll just rewrite it here. If we were to look back at our equation, we've now increased the concentration of H plus in solution, so that means we're going to favor our deprotonated form. So when the pH is less than the pKa, we're going to be favoring the protonated form. Now, there's also an OChem way you can explain it based on acid strength. So when your pH is less than the pKa, you're effectively saying that the acid strength of the solution is stronger than the acid strength of your acid. And your equilibrium always favors the weaker acid. And so you'd be favoring the functional group protonation because it's the weaker acid. But if you haven't taken OChem, that would make no sense. So don't worry about it. But in terms of what we need to know, when pH is less than the pKa, we're increasing the H plus concentration. So we're going to shift the reaction to favor the protonated form of our functional group. Okay, so when pH is less than pKa, we're favoring the protonated form. Now, I'm going to write HA, but I also want to recognize that HA is not the only protonated form we have, right? We also have our RAH3, where this is more of our carboxylic acid, and this is our amine. Okay. Okay, so moving on to our third step, we're going to say our pH is greater than our pKa. Now, it's either, well, we have three options here, right? We have pH is equal to pKa, where they're equal, pH less than pKa, where the protonated form is greater. By logic, when the pH is greater than the pKa, we must be favoring our deprotonated form. But logic is great and all until you get to an exam and logic goes out the window. So to show this, right, let's look back at our equation. Okay, we're having a greater pH than pKa, so from solution, we're decreasing our H plus concentration because we have a greater pH. So we're going to be shifting our reaction over, which means we're favoring our deprotonated form. Okay. So that's why we're favoring our deprotonated form. Goes back to Le Chatelier's principle. And now what we can do is we can say our pH greater than pKa are going to be favoring our deprotonated form for our carboxylic acid, like that. For our amine, looks something like that. Okay. And with amines as well, you have to be always wary of perhaps you have an amine looks something like this. Okay, where a protonated would have one hydrogen and a deprotonated might have none, but it has its 3 bonds. Okay, so that's something to always be wary about with amines, especially in things like histidine, where, so if we look at the what's it called? The structure of histidine. Oh my god, I hate drawing histidine. There we go. It should be like that. Nitrogen there. There we go. So if we protonate this, notice how the protonated state has a nitrogen here that only has one hydrogen attached to it. Okay. But it has 4 bonds. It has 1, 2, 3, 4. So let me do that a different color. One bond, 2 bond, 3 bond, 4th bond. Okay, so that's something to always remember with our amines, what it means to be protonated and deprotonated, especially because we talk about carboxylic acid so much. Okay, so for our questions, for 8, circle protonated or deprotonated at a pH below the pKa. So we are dealing with this guy here, pH below pKa. Which form of the base will be more common? We're going to be favoring the protonated form. At a pH below the pKa, which form of an acid will be more common? I don't know why they structured it like this. That's odd. At a pH below the pKa, it's protonate. Yeah, when they're saying base, they're referring to the amine. At a pH below the pKa, which form of the base will be more common? Yeah, it's... That's so weird. I don't know why. Okay. I don't know why they structured it like that. If we look at our amine reaction, right? If we have a pH below the pKa, we're increasing the amount of H+, so we'd be favoring the protonated form. I don't know why they split it up like that. Okay. Fascinating. Anyways, they're both protonated. And then for question 9, when pH is greater than the pKa, doesn't matter acid or base, we're decreasing the amount of H+, so we're going to favor the deprotonated form. Yes, what is your question? I might have an answer. Hello. So technically a base is something that would accept the proton. So in a solution, when you have a base, this is something that can accept a proton. So this would be considered a base. That would be considered a base. What's another good base? I guess the stereotypical base is OH minus. So NaOH is like the base when you get in Gen Chem. Yeah, so acids are H plus donors. Bases are H plus acceptors. So this OH minus can grab an H plus to make H2O. Technically, what we should be saying is the protonated form is actually the acid form. That's why I'm not completely sold on how they worded this, but I didn't make it, so whatever. The protonated form is the acid form. The deprotonated form is the base form. That's the most technical way to describe this. So the protonated form is acid. Mm-hmm. Yeah, but I think what they're trying to get at is they're trying to say amine equals base, carboxyl equals acid, which isn't always true, but whatever. As long as you understand that your amine will do this reaction and your carboxyl will do this reaction. That's what we care about. If you remember those two reactions, that's good. But yes, acids are the donors, bases are the acceptors. Also, fun fact, this can actually this can be a base. It can pull up a hydrogen on this lone pair to give you that. That's well beyond the scope of this class. That's 118C for OChem, but it's technically true. Okay, so then we move on to the practice test questions. And find more space. Okay, so question 10. We're dealing with, that is glutamic acid. Okay. And now it's asking for, at this pH, or for this protonation state, okay, what is the pH associated with this? Or a pH range. Okay, so for glutamic acid, it's kind of in the middle. We can see the pKa of the carboxyl group is 2.19. But now we have two carboxyl groups, right? So which one is it referring to? Well, we can look at the chart and we say pK1 is a carboxyl group, pK2 is the amino group, and pK3 or pKr is for the R group. Okay, and we know this to be the R group because to find the R group, right, we find our backbone. We see our N, C, C. So this here is our backbone, which means that this functional group is 2.19, has a pKa of 2.19. Then we have 9.67, and then 4.25. Okay, so the pH for this, let's see. We have a carboxyl group that is deprotonated. Sorry, protonated. Oh my God. A carboxyl group that's protonated. For this to be protonated, what must be true of my pH if my pK is 4.25? The pH needs to be less than the pK, right? That's the only way to get our protonated form. Be dominant. So pH less than pKa, or protonated form is dominant. I have a question. Can deprotonated of this group still exist in a solution when the pH is less than pKa? So if I had, let's say my pH here, because we know it needs to be less than the pKa, which is 4.25, at a pH equal to 4, I know my dominant state will still be protonated, but will I have some deprotonated molecules as well? Yes, that is correct. So we will still actually have a few molecules that are deprotonated. That's why I'm specifying dominant state. Now, the general rule is when you get to about 2 pH units below or above the pKa, you can assume 100%, which is not going to be covered in this class. But that is something I want you to be aware of, is it's still possible to have deprotonated forms. It's just nowhere near as many as the protonated. So our protonated is our dominant state. And whenever you're asked to calculate the net charge of a molecule or an amino acid at a given pH, it's referring strictly to the dominant protonation states. We're not going to get into partial charges. That is for BIS 102. Okay, but anyway, so our pH has to be less than our pKa. If our pKa is 4.25, we know our pH has to be less than 4.25 in order for this functional group to work. Okay, now let's move on to our second one, our amine. Is our amine protonated or deprotonated? It's protonated. So if it's protonated, what must be true of my pH? Does my pH need to be less than, equal to, or greater than my pKa? Less than. So our pH needs to be less than our pKa. Oh, that looks like an A. There we go. Okay, so that means my pH needs to be less than 9.67, which doesn't really help because I already knew that it needs to be less than 4.25. But there's reasons why we go through all of this. Okay, and then finally for our last one, is my carboxyl group protonated or deprotonated? This guy here. We got conflicting answers. Ooh. So this is protonated. We have our OH. Okay, so we have our hydrogen attached to our carboxyl group, so this is protonated. And so if this is protonated, what must be true of my pH? Does it need to be less than, equal to, or greater than the pKa? pH needs to be less than pK. Nice. Okay, and so that means our pH needs to be less than 2.19. So now what we can do is we can take all these together and find where they overlap. Okay, so I have a pH less than 4.25 and a pH less than 9.67. If I have a pH of, let's say, 3, does this match these two at least? Well, yes, right? It is less than 4.25 and it is less than 9.67. Does it match this third one, though? Is a pH of 3 less than 2.19? And it's no. Okay. And so we keep doing this, or we can put it on a number line. So you could do it like this. So 2.19, 4.25, and then 9.67. And we'll say, okay, we know it needs to be less than 2.19 for the first group. It needs to be less than 4.25 for the second group. And we know it needs to be less than 9.67 for the third group. And we're looking for where all of them overlap, which is there. Okay. So our overall pH, to answer this first part, our pH needs to be less than 2.19 because that is where our overlap is. How's that feeling for everyone? Good, bad, terrible? Any questions? Cool. Ooh, maybe question. This is question 10, first molecule. So now we just get to do this same process over and over again. So for the second molecule, we have oh yeah, there's a very high chance this is going to be, I mean, this concept is 100% going to come up on your midterm quite a lot. Maybe it's not this exact style of question, like finding a pH range, but there's going to be variations of this. You're going to be tested on this. So definitely know this. And if you don't, there's going to be the in-person pH and pKa reviews done by Usman, who's way better than me. And what's it called? You can go to TA's office hours, go to Dr. Fachadi's office hours. All those are going to be great. Okay. But okay, so now for our next one, right? Keeping our pKa's, I think it was 4.25. 4.25, 9.67, and 2.19. Okay, so starting with our R group. We are protonated, so what must be true of our pH and pKa? So in other words, is pH less than, equal to, or greater than pKa for our R group? Less than, very nice. So our pH must be less than 4.25. Okay, for our amine, we're protonated. We can use the exact same logic as before. Our pH must be less than our pKa. So our pH must be less than 9.67. And now, when we look at our carboxyl group, is this guy protonated or deprotonated? This guy here. This is deprotonated. And so what must be true of our pH and pKa? Is pH less than, equal to, or greater than pKa? pH is greater than pKa. So that means my pH needs to be greater than 2.19. So once again, putting my stuff on the number line, we have 2.19, 4.25, and 9.67. This is personally how I solve these types of questions, but you can, do whatever you want. Whatever works for you. Like, whatever makes sense for you. This is just how I personally solve it. So we know my pH for the lower one needs to be greater than 2.19. It needs to be less than 9.67. And it needs to be less than 4.25. And we're looking for the point where all three overlap, which is this range here. Okay, so if we plugged in pH of 3, pH of 3 is less than 4.25, checks out there. pH of 3 is less than 9.67, checks out there. And a pH 3 is greater than 2.19, checks out there. Okay, so our pH range is going to be greater than 2.19, but less than 4.25. And that would be our pH range for this protonation state being dominant. Any more room? Okay. So the next one has here, and then we were dealing with 4.25, 9.67, and 2.19. All right, our R group, protonated or deprotonated? Deprotonated. And so, what is true of my pH and pKa? Is pH less than, equal to, or greater than pKa? Greater. Very nice. So it's greater than pKa, and so that means my pH must be greater than 4.25. Looking at the amine, my pH, pKa, let's see, I have a protonated amine, so that means my pH must be less than my pKa, so my pH must be less than 9.67. And then finally, my carboxyl group, my pH must be greater than my pKa to get a deprotonated carboxyl group. So my pH is greater than 2.19. Okay, so then looking at our number line again, 2.19, 4.25, and 9.67. We know it must be, what, greater than 4.25? Must be greater than 2.19, and it must be less than 9.67. So my overlap is here. So my pH is going to be between 9.67 and 4.25. Okay, and then the final one. All right, 4.25, 9.67, and 2.19. So my R group is deprotonated. So my pH needs to be greater than my pKa. So my pH needs to be greater than 4.25. For my amine, is my amine protonated or deprotonated? It is in fact deprotonated. Okay, so in order to get a deprotonated of my amine, what must be true of pH and pKa? Is pH less than, equal to, or greater than the pKa for this amine to be deprotonated? Must be greater. Correct. So our pH must be greater than the pKa in order to get a deprotonated functional group. So that means my pH needs to be greater than 9.67. And then finally, for my third one, pH, pKa, my functional group is deprotonated, right? My carboxyl group. So is a pH less than, equal to, or greater than the pKa? greater than. Yep. So our pH must be greater than our pK, which means my pH must be greater than 2.19. And now, final time, get our number line, 2.19, 4.25, and 9.67. It has to be greater than 2.19. It has to be greater than 4.25 and greater than 9.67. And the overlap of all three is right here. So my pH needs to be greater than 9.67. Any questions? Okay. So the next one, question 11, says draw what lysine will look like at these different pHs. So lysine, I'm going to draw it completely protonated. So this is a completely protonated lysine. 1, 2, 3, 4. Okay, so this is lysine. At a pH of 1. Let me write your pKa's. So the pKa of lysine is 2.18 for the carboxyl group, 8.95 for the amino group, and the R group is 10.53. Now, at a pH of 1.5. Let's see. Let's start with the R group. Is pH 1.5 less than, equal to, or greater than the pKa of my R group, which is 10.53? So pH is less than pKa, and if pH is less than pKa, should my functional group be protonated or deprotonated? Should be protonated. So that would be my R group. Okay, now we'll go to the amino group. pH 1.5 and pK 8.95. Should my functional group be protonated or deprotonated? Protonated. Okay, and finally my carboxyl group. pK 2.18, pH 1.5. Should my carboxyl group be protonated or deprotonated? Protonated. Very nice. So at pH 1.5, all of our groups are completely protonated. Okay, how about a pH of 5? So draw everything out. Okay, starting with our R group. Should my R group be protonated or deprotonated? Why do I see deprotonated? So our R group pKa, right? Remember, our R group is this guy. Our R group pKa is 10.53. Our pH is 5. Which one is greater, pK or pH? Our pKa is greater. So if our pH is less than the pKa or pKa is greater than the pH, does that favor protonated or deprotonated? Protonated. So this guy will be protonated. Does that make sense? Perfect. Okay. Now for my amino group. My pK is 8.95. My pH is 5. Should my amino group be protonated or deprotonated? You were actually right the first time. So yes, it should be protonated because our pKa is greater than our pH. What I honestly recommend doing is writing out all of this. Keep track of it, making a graph or a table or whatnot. That way you can keep track of this. So here my pK is greater than my pH, so I should be protonated. And I'll say this is my R group. This is my amino group. This is my carboxyl group. Like that. And then you could even draw out. I should have H3NR plus, H3NR plus. And then finally, we have a pK of 2.18, pH of 5. Should my group be protonated or deprotonated? My carboxyl group. Deprotonated, right? Because 5, the pH is greater than the pK. So I should have a deprotonated. Oh, what did I do? Uh-oh. Okay, deprotonated. And so my R group, or sorry, not my R group, my carboxyl group should look like that. Okay, so this would be pH 5. And then finally, what's the other one? pH 10. All right, let's go through again. So my R group, amino group, carboxyl group. I'll do, you know what, because I always compare pH and pKa with pH first. I'll do that. So my pH is 10. My pKa's are 10.53, 8.95, and 2.18. Okay. Okay, for my R group, pH, pKa. Is pH or pKa greater? pKa is greater, so that means I should be doing with a protonated or deprotonated R group. Protonated, very nice. So my R group, like that. You might be wondering why I keep switching things up. So comparing pKa to pH, pH to pKa, switching up the orientations of my R groups. That is so you guys get used to seeing these things asked in a bunch of different ways. Because there's a million ways you could ask these questions, a million ways you can compare them. Is pKa greater than pH? Is pH less than pKa? That sort of thing. Okay, so then for my amino group, is my pH or pKa greater? So that is supposed to be an 8. My pH is greater. Should I be protonated or deprotonated? Deprotonated. So my R group looks like that. Okay, and finally, for my carboxyl group, pH or pKa greater? My pH is greater, right? Because I'm dealing with 10 and 2.18. So should my carboxyl group be protonated or deprotonated? Deprotonated. So we look like that. Okay. The final question is a really good application question. So, there we go. We have, oof. Oh, am I going to have to draw this? Okay, hold on 1 second. O minus, and perfect. Okay, so there's our substrate. And then we have a lysine residue here, an arginine residue here, a histidine residue here, his, and then glutamic acid, aka glue here. Okay. Really quickly, lysine's residue, because we only care about their R group interactions, looks like this. Arginines, looks like that. Histidine, what's it called? Oh, shoot. Pencil. There we go. There we go. That's what histidine looks like, and then glutamic acid. Actually, I'm going to redraw histidine really quickly. Hold on. Two, three, four. There we go. It's very scuffily drawn, but it'll get the point across. No, this looks disgusting. I hate drawing histidine. It's one of my least favorite ones because it's a 5-membered ring. And I suck at drawing 5-membered rings. I don't know why. But I've never, ever been good at it. Oh my gosh. Good enough. Okay, there's histidine. So, the question asks us, rank the following pH levels in order from best to worst ability to bind the molecule. Okay, and then we're dealing with pH of 3. pH 5, pH of 7. Nope, 9. And the R group residues are here's our pKa's are 4.25. Histidine, it should be like 6 point something. They are saying 6.00. Arginine should be like 12. What did they say? 12.48. And then lysine is 10.53. Okay, so we want to take note of our interactions here. Between this lysine residue and the substrate, we see a negative charge on the substrate and a positive charge on lysine. So that means we want this ionic interaction to take place, right? Because ionic interaction, binding, right? We're trying to get these things to bind together. We want them to have interactions. So for lysine to have a positive charge, what must be true about my pH? So in other words, how must my pH compare to my pKa if lysine has a positive charge? Well, the first question we should ask, pH is less than pKa. Okay, nice. So we know this is deprotonated. This is protonated. Okay. To get a protonated amino acid, we need the pH to be less than the pKa. Okay, so that means I know my best binding is going to occur for at least this residue when the pH is less than 10.53. Okay, now let's look at arginine. Arginine here, is arginine protonated or deprotonated? So, oh, yep, very nice. It is protonated. So this one's kind of tricky. But what we see is we have an amine of sorts with a positive charge. Okay, so a deprotonated arginine will look like this. That would be a deprotonated arginine, where it just has one hydrogen attached to the double bond end. Oh, also technically there's a hydrogen there. That's what I forgot that as well. Whoops. My bad. Okay, so this arginine is protonated. Now, to get a protonated arginine with a pKa of 12.48, what was my pH range be about? In other words, should my pH be less than, equal to, or greater than my pKa? To get this guy to be protonated. Less than. Very nice. Okay. Now we look at histidine. Let's think about this. We have two positive charges here. What do positive charges want to do? So if you get two positive charges in close proximity, what do they want to do to each other? Or what interaction will they have? It won't be ionic, right? Because you don't have a negative charge, but they will want to repel. Right? Would this be, do you think this would be good for binding? Right? Would there be an ionic bond here? No. So would this stabilize or destabilize the binding of this molecule to our protein? It would destabilize it. So that means we want no positive charge, aka we want a neutral. Because if it's neutral, we can have hydrogen bonding, right? And we just have that hydrogen bonding. We don't have to have hydrogen bonding competing with repelling like charges. Okay, so if we want neutral, does that mean we want a protonated or deprotonated histidine? We want a deprotonated. Very nice. So if we want a deprotonated, how should my pH and my pKa compare? My pH needs to be greater than my pK. So in other words, my pH should be greater than 6.00. All right, finally, moving up to our glutamic acid. We see positive charge on the molecule, negative charge on our protein with glutamic acid. Is this a beneficial? Would this interaction facilitate binding? Yes. So we want to keep it like this. So if our glutamic acid is deprotonated and we want to keep it that way, should my pH be less than, equal to, or greater than our pKa? Want it to be greater. Okay, so now we need to take all of this together. We have, for best binding, we need our pH to be greater than 10.53. We want our pH to be, less than 10.53. pH needs to be less than 12.48. It needs to be greater than 6 and greater than 4.25. So let's see. Which of our pH options here matches this, if any? pH 9. Okay, so 9 is less than 10.53. It's less than 12.48. It's greater than 6, and it's greater than 4.25. So 9 would be our best. Which color do I want? Use orange. So this would be number 1. Okay. How about a pH? How about 5? Is a pH of 5 less than 10.53? Yes. Is it less than 12.48? Yes. Is it greater than 6? No. Is it greater than 4.25? Yes. Okay. And then how about a pH of 3? Is it less than 10.53? Yes. Less than 12.48? Yes. Is it greater than 6? No. And is it greater than 4.25? No. So, which one would you say would have better binding between 5 and 3? I'd say probably 5. You could maybe make an argument about the negative charges, the positive charges repelling, but I think that is well beyond the scope of this class, and we're just trying to get you to see stuff like this, where it's, hey, multiple interactions are not as we would like. Okay, so pH of 5 would be probably our second one, our second best, and then a pH of 3 would be our third best in terms of binding capabilities. Does that make sense? Are there any questions? Okay. So what we'll do now, because I want to try to end at 3, that way I'm not taking up too much of your guys' day. I'm going to kind of pick and choose questions from my workshop, which the link is in the video links and practice exams tab. And we're just going to go through a few of them, the ones that I feel are most important to talk about or most interesting to talk about. And then I'll post the key for the rest of them later. And if you have questions about them, you feel free to shoot me a message and we can discuss them. Okay. Question 1, we've already kind of talked about. Question 2 is very similar to question 1, but it's from the opposite way. So it says a 10 times decrease is what? So essentially, which of the following scenarios is a 10 times decrease? So A says protons are added to a solution to change the pH from 3 to 4. What are we thinking? Could that be the answer to this? Also, I'll give you guys a minute to pull up the worksheet. What is your reasoning for yes? So since the difference in pH is about 1, we know that as pH increases, the concentration decreases. That is correct. But there's an issue. Your logic is absolutely perfect. Yes, so the question is talking about that, but if pH increases, concentration decreases, that implies as pH decreases, concentration increases. There's an issue though. A says protons are added to a solution. Would adding protons to a solution decrease the pH? No. So your logic is absolutely correct. If it had removed the first part of that sentence and just said, change the pH from 3 to 4, you would be correct. Because that would be a 10 times decrease in pH. But, oh wait, hold up. Sorry, I got it backwards. The 3 to 4 part is the wrong part. Protons being added to the solution is the correct part. Sorry, I don't remember my own questions. I was saying there's another answer choice like that where it has it flipped. Okay, so a 10 times decrease in pH would be associated with protons being added to the solution, but it wouldn't change the pH from 3 to 4. Hold up, wait. A 10 times... I just realized my question's wrong. Hold up. I realized it's wrong. It should say... That's what it should say. Oh my gosh, there's no way. Crap, dude. I did not proofread this at all. You'll have to forgive me. Okay, if you could change that, that would be great. I appreciate it. Sorry about that. It should say, okay, take two. In my defense, I actually made this during lecture. Actually, that's not a defense at all. Okay, hold on. So, question 2. A 10 times decrease in H plus concentration. There we go. Okay. So A says protons are added to a solution that would result in an increase in H plus concentration, but that would change the pH from 3 to 4. So A is wrong. B says protons are added to a solution. This would decrease the pH, and it would change it from 9 to 8. Could B be correct with my updated question? So, if protons are added to a solution, would this decrease the pH? If we add protons to a solution. Oh my God, I can't keep. Perfect. So, if protons are added to a solution, it would decrease the pH. But our question is asking a 10 times decrease in H plus concentration. So B would be wrong. Hold on. I don't think there is even a right answer for this question. Oh my God. Okay, so this is why I proofread my questions. Oh my gosh. Okay, they're all wrong. they're all wrong. Hold on. Let me go grab. I'm gonna fix this question. I promise you that was not intentional. I absolutely promise you that was not intentional. Crap, dude. Sometimes my brain just does not work. Uno momento. Sometimes my brain, no brain. Okay. And plus yes, okay. This should work now. Oh, I had Longacre for Chem 2C. Don't worry. I understand. It was a lot of fun. This is why we proofread. I think one time, one of my practice exams, I had like 20 revisions. It was bad. Okay. Take 2. Hopefully I don't come across any more errors. God dang it, dude. Okay. So, now that we have a question that actually works, did Singer mess up his exam questions? Yes. Constantly. All the time. So many questions had errors. It was bad. Either grammatical errors or, yeah. If you ever want to laugh one day, you can ask me all the stuff he pulled, because it's incredible. Okay. A 10 times decrease in the concentration of H plus would be associated in which of the following scenarios? A says protons are added to a solution to change the pH from 3 to 4. pH from 3 to 4 does check out, correct? Right? A decrease in H plus would increase the pH, but it doesn't make sense to add protons to the solution. And in fact, A, B, and C, we can all cross out because they say protons are being added to the solution. And this would be wrong, right? Decreasing the H plus concentration would mean removing H plus from the solution. Okay, so it doesn't matter about the pH change. That part is wrong. So A, B, C are all wrong. And then we just have D and E left. Yes. So D says protons are removed from the solution. That checks out. But son of a bitch. I changed the wrong answer choice. The best option. That's terrible. Oh my god. I'm so sorry, guys. I even had a thought of I should probably proofread these questions, and then I got cocky and was like, nah, I'm good. I don't need to. It's actually, okay, hold on. I have a story about Singer if you guys want to hear. So, during my quarter, when I took the class, very, very long time ago, there were a lot of mistakes on his exams. And so what he did, because he didn't want to deal with all the regrade requests, he gave us all 2 questions, free points. Okay. So I think each question was worth like 5 points. So he gave us 10 extra points. He said, if you submit a regrade request, you automatically lose those 10 points. So that was the curve for our class, or at least for the first mid. Actually, no, it was for both the first and second midterm. Singer is incredible. I think he's actually, in terms of content covered, he's the most like middle ground, like fairness. But man, he's got an interesting personality. Oh my god. It's incredible. It's incredible, dude. Oh my gosh. Okay. Okay, take 3. Take 3 says D, protons are removed from a solution to change the pH from 6 to 7. This would be a 10 times increase. So protons are being removed. That is correct. And a 10 times increase would be 6 to 7. So that works. Originally, when it was 6 to 8, that would be a 100 times increase. And that would be wrong. And then E says protons are removed from a solution to change the pH from 8 to 7. That would be associated with a 10 times increase in H plus concentration. So the answer choice for 2 is D. That was way more painful than it was supposed to be. Okay. Okay. We're okay. We're okay. I'm good. Anyways. How are we feeling about question 2? Now that it's actually correct, does the question make sense? Now that it's been updated. Perfect. Okay. Really quickly, I want to go over. Let's go over question 3, and then I'll call it. Does that sound good? And I mean, you're welcome to leave if you want to. I'm not going to keep you here. But let's go question 3. So question 3 says, we have a hypothetical reaction. A plus B goes back and forth with C plus D. Okay. And we have between times T equals 3 and T equals 5, there is no measured change in concentrations of these guys. Okay, what does that tell you about what's happening between time 3 and time T equals 5 seconds? What state would we say this reaction is at? If there's no measured change in the concentration of either 4 entities. Does it say that A plus B equals the concentrations of C plus D? No, so they're not equal. But yes, they are at equilibrium. So we are at equilibrium at time T equals 5 seconds. Now, between times T equals 7 and T equals 9 seconds, we see the concentration of A is increasing. However, we don't know the concentrations of B, C, or D. Right? Those we don't know. B, C, or D. We only know that the concentration of A is increasing. Now we got to figure out which of the answer choices works. So A, more of A was added. Well, okay, so if more of A was added, would we see, so at T equals 6, A was added, would we see the concentration of A continue to increase between T equals 7 and T equals 9 seconds if A was added at T equals 6? So in other words, if we increase the amount of A, would we keep seeing the concentration of A increase? Someone says no. Do you guys agree? Yes, so they are correct. And that's because, right, Le Chatelier's principle, if we add more of A, we'd shift the reaction this way. And so we wouldn't see more of A being created. We'd see the concentration of A start decreasing. Right? So we'd have a certain amount, we'd increase it, and then we'd start to see it decrease. So if this were the concentration of A, we'd be at a certain amount, we added to it, and then it would be decreasing. So A doesn't make any sense. Or it doesn't fit our Le Chatelier's principle. B says more of B was added. Okay. So if B was added, we'd be increasing the amount of that. Would we see the concentration of A start increasing? No. Because just like when we increase the amount of A, we're increasing the amount of product we have. So it'd be, the amount of reactant we have. So it'd be increasing the amount of products for our forward reaction. So B doesn't work. Okay. How about C? More of C was added. So let's see. We'll write it all out again. If we increase the amount of C, what would happen to our concentration of A? More A would be produced, right? Because we'd have a net reaction, right? Our reverse reaction would be favored, so we'd start increasing the amount of A. And does that fit our postulate in our question? Yes. So C would be correct. How about D? So D was added. C plus D is the same thing as C, right? We're increasing the amount of D. We'd shift the reaction backwards to produce more A. So D is correct. And so both C and D are correct. That gives us E as our best answer. So the correct two choices are C and D, making E correct. The reason why I left it in terms of A plus B goes to C plus D is you could get this question and it can be talking about carboxylic acids, it could be talking about amines, it could be talking about any variant of our acids and bases that we want, right? And so a huge chunk of problems you'll encounter can more or less be boiled down to using variables A, B, C, and D. And then we're just substituting in specific molecules for those variables. That's why I chose to do A plus B goes to C plus D instead of doing, a carboxylic acid and water being the two reactants. Two reactants for the forward reaction. Okay. But this just goes back to Le Chatelier's principle and equilibrium. Okay. For questions 5, 6, 7, 8, and 9, this is a very common test question I see, and it more or less is exactly what we did earlier with these guys, right? Where we figured out at what pH or what lysine would look like at the different stages, right? It's just this, except instead of having the molecule, we're taking this lysine or this amino group, the R group has a +1 charge. This amino group has a +1 charge. Carboxyl group has a 0 charge, so you add them up. 1 + 1 + 0. So the overall charge on this molecule is +2. It just is this exact same thing, except instead of doing dominant state, the drawing, you're summing up all the charges on that molecule. Does that make sense? And then 10, 11, and 12 are fun application questions. 11 is probably one of my favorite questions. Dominant protonation state is referring to, is the deprotonated or protonated state more abundant in solution? So it's not dominant protonation, it's dominant protonation state. And like I said, what that means is that whichever one, either the deprotonated or the protonated form, is more abundant in solution, that is the dominant one. So if you're, what we're talking about here, right, with our pH and pKa, we're saying that, where is it? Go. What the heck? Oh, well. So when we're saying our pH is less than our pKa, means protonated, what we're saying is that the dominant protonation state is the protonated form. And when pH is greater than the pKa, we're saying our dominant protonation state is deprotonated. When it says side chain, yes, it's asking about the R group. Yeah, so dominant protonation state is just referring to which protonation state, protonated or deprotonated, is more abundant in solution. And then side chain, the reason why I threw that one in is you will see side chain, R group, residue, all of those things are all different ways that you can be referring to that thing sticking off the backbone. Although residue has one other caveat in that it must be part of a peptide. But those are all ways that you might see them written. Would I be able to do number 9? Yes. Which is number 9? Okay. Histidine at pH 14. So, you're going to make me draw histidine. Darn it. Okay. Actually, I did give you guys all the amino acids on that last page. They're all, what's it called? Drawn below with their pKas as well. So, histidine. Gosh. Yes, I should have written at the bottom there, or somewhere on the top that if you scroll down to the very bottom. It should be that. Yes, that's histidine. Okay, and then hold on, I need to pull 6.04, 9.09, and 1.7. Okay. Question 9 asks for which is the correct charge for histidine at pH 14. So at pH 14, let's go through. We have our R group, we have our amino group, and our carboxyl group. Okay, our R group. We have pH, pKa. Our pH is 14 for all of these. Our pKa is 6.04. Okay. So now, which is greater, pH or pKa? pH is greater. So if pH is greater than pKa, are we protonated or deprotonated? So we're deprotonated. What is the charge of this functional group? And I'll give you a hint. It's based around this nitrogen here. Nitrogen with 3 bonds versus a nitrogen with 4 bonds. So should my deprotonated state have a positive charge or should it be neutral? Should be neutral. So that means it would be a +0 charge. Okay, for the amino group, my pKa is 9.09. So should I be protonated or deprotonated? I guess deprotonated, correct. And that's because 14 is greater than 9.09. A deprotonated amine is neutral, positive charged or negative charged? Neutral. So +0. And then finally, we have our carboxyl group, 1.7. 14 is greater than that. That means we're going to be deprotonated. And this is a carboxyl group. So what charge will my carboxyl group have? -1. So it'll be charged with the -1. Now we can sum that all up. 0 plus 0 plus a -1 is equal to -1. So our answer choice would be B. Does that make sense? Really, 5, 6, 7, 8, 9 are the exact same process over and over and over again with just different amino acids at different pHs. That's all. So to be honest, I could give you all 20 amino acids at a plethora of different pHs. And to be honest, that's what I did. For these questions, I just copied and pasted and just changed the amino acid and the pH. Because that's honestly how these questions work. It's the same thing over and over and over again with just different amino acids and different pHs. Okay. Are there any other questions? Also, I'll make that note. Chart with pK. Wait, would the answer change if you didn't state that it was a dominant protonation? Actually, yes. For this one, no. Actually, for this, well, wait, hold on. What was my pH? This one would not change actually. Once you hit upper div, you'll start to do pH is equal to pKa plus the log of the A minus over HA. And then you use that to calculate how much of each you have. And then that's what you multiply. So if you had like 80% of your A minus and 20% of your HA and you were dealing with an amine, you would have 80% that are neutral. So for the amine, oh, where's my cursor? Neutral for an amine. And then 20% with a +1 charge. And so you'd have a +0.2. Now, for this question, I had said earlier that about 2 pH units above or below the pKa, you can assume dominant protonation state. So this one, it wouldn't matter. Aspartic acid. So question 7, 8 would maybe not 8. I think 7 would be slightly different. 6 would be slightly different. And 4. I don't remember phenylalanine's pKas off the top of my head. Maybe phenylalanine as well. But we won't ever touch that in this class. in this class, you will always assume the dominant protonation state. So if the protonated state is, even if you had 100 molecules and 51 of them were protonated and 49 of them were deprotonated, you would assume, in terms of calculating overall charge, you would assume protonated because there's more protonated than deprotonated. So always assume dominant protonation state in this class. Mm-hmm. Of course. I'll just chill in here. If you guys have any more questions, you can either unmute or put them in the chat. But if you don't, you are free to go. Of course. Anytime. Thank you. You too.